All right, so we're going to look at number 3 from homework number 2, and this one says that you have a 10-kilogram bowling ball connected to a vertical spring that's oscillating. We are told this piece of information, that the student was able to graph it to this equation. Now, we do need to extract information from this equation because we know that a position versus time is going to have the amplitude times either sine or cosine of the angular velocity times time. Sometimes it's written in what is this, function notation like this. Sometimes you will see this as 2 pi f times the time. So all that information is okay, and like I said, sometimes sine, just depending on where it starts, you might use a sine or not. You can also have a phase shift, so you could have it shifted over. So if you see like over here, you see like a plus some angle, that's totally okay. Nothing's going to change that. But these are the main key pieces that we need. So from this equation, we know 0.5, that's in front, so that has to be our amplitude. So we are told that our amplitude is 0.5. We are also told that 2 is in front of the t, so that has to be our omega. So the angular velocity is 2 radians per second. Now that part is going to help us in the second part here because it says find the period for its motion. So we're looking for capital T, find the period. I know that omega is the change in our angle over time. And so if we make one full rotation, one full angle is 2 pi radians. And the time it takes to complete that full rotation is capital T, the period. So if we plug this information in, we have that 2 is equal to 2 pi divided by the period. Well, multiply by t, so 2t is equal to 2 pi. Divide by 2, and your period is going to be pi seconds, or 3.14. Either one is okay. To get the maximum speed attained by the ball, we're actually going to be using our equations that are very similar to the uniform circular motion. So in uniform circular motion, that we had that the velocity is r omega. The difference is when we're talking about simple harmonic, instead of just a circle, that radius becomes the amplitude. Well, we know what our amplitude is. Our amplitude is 0.5. And then omega is going to be 2 radians per second. So it's really just 0.5 times 2. Well, 0.5 times 2 is 1 meter per second. Next thing we have is the max acceleration. Acceleration, again, there's several different equations you can use here. I would use my v squared over r. But again, instead of r, we have the amplitude. So we're just going to replace that with an a. We know what the velocity is. That's just 1. So we have 1 squared divided by 0.5. Well, 1 squared is 1. 1 divided by a half is 2. So then the max acceleration is 2 meters per second squared. The next is looking at the total energy of the system. The total energy of the system should be constant throughout. E is constant. Now, we can choose at any location, but the easiest one, if we know the max speed, is going to be the energy at its max speed, because all the energy has to be kinetic energy. So I'm going to say that E total is going to be 1/2 mv squared. I know that the mass is actually told right here. So I have 10 kilograms for the mass. And I know that the velocity from before was 1 meter per second. So we have 1/2 times 10 times 1. 1/2 times 10 is just 5. So we have 5 joules of energy total. The last thing is the spring constant. The spring constant is also called the force constant if you're dealing with something that is not a spring but acts the same way. That is the letter K, lowercase k. Again, don't get confused by kinetic energy and lowercase k. In this case, lowercase k is going to represent it's going to be represented in two equations. You have either the force of a spring or you have the elastic force. In this case, the easiest one to look at is the elastic force. So if we look at the total energy, now this is going to be when it is at rest, when it is stopped. So all the energy is converted from kinetic into elastic potential. So all the energy is going to be 1/2 kx squared. Now, since it's at that amplitude, it's at that max displacement away, instead of saying x, we're going to replace that with a. Now all I have to do is plug in my info. So I know that my energy is going to be 5. K is what I'm looking for, and my amplitude is 0.5. If you multiply by 2, we're going to have 10 is equal to K. 1/2 squared is the same as 1/4. All you have to do is multiply by 4, which tells me K is going to be 40 newtons per meter. Great, we've done the hard part. We have all of the calculations. Now what we have to do is graph it out. So over here, we're going to start with our displacement versus time. Now we are starting at some location. You will notice there's no phase shift here, so that means we're going to start at either the amplitude or 0. We're not shifted up or anything like that. So over here, we're going to graph out the displacement versus time by finding originally where we're going to start. It is a cosine graph, so if you know what a cosine graph looks like, we're going to start at +1. Now in this scenario, if you didn't know that, you can, since you have the equation, you can always plug it right in. So if we started with our 0.5 times the cosine of 2t, if we said let t equal 0 and we plugged 0 into our equation here, we would have 0.05 times the cosine of 2 times 0, which is really just 0. Well, cosine of 0 is 1, so that tells me that my position at 0 seconds is 1/2. That is a positive 1/2, which means we're going to start in the positive direction. Now from here, we know that 1 full cycle is going to be, essentially, I'm just going to say this is 3 just for ease, but it'll be 3 and some change. So we would go a little bit past 3. I'm just going to start there. That means that every 3 seconds, we're going to get to that same exact location. It'll be 1 full cycle every 3-ish seconds. That also means that halfway, so 1.5 seconds, I should be in the total opposite location. So I should have an amplitude in the other direction. So that would also mean 4.5 seconds, I'd have an amplitude down here. And also 7.5 seconds, I'd have an amplitude down here. Again, you should really have that shifted over a bit just to account for the 0.14. But for all intents and purposes, we'll still be able to see it, and it'll be a little bit easier to see here. All right, now again, we're going halfway. Halfway, we will be halfway. So these are kind of good markings to make just to kind of help you draw it, just so that everything is kind of in that same orientation, that same angle. All right, now that we have all our dots, now we're going to actually fill in the graph. Now you're going to start kind of flat, and then it's going to curve down until it's pretty straight, and it's going to do the opposite in this kind of S-like shape. And then we're going to repeat. So now we're going to go kind of flat, and then we're going to curve up. From here, we're going to start curving back down, and that is just going to continue to repeat. It doesn't have to be perfect, but it does need to look like it's actually curving in your graph. I don't want to see any lines that are just jagged and straight. That is not what we're looking for. Perfect. Once we have this, now we're going to go into the velocity versus time graph. Now, to go from position to velocity, we want to make sure that we are checking the slopes. This is the slope of the tangent line. Now, what I mean by that is if you were to draw a line that just touches the curve, that's right at that location, we want the slope of that line. So all of these guys are at the very top. If you were to draw a line right there, the slope would be 0. So at each of those locations, which was at 0 seconds, at 3 seconds, 6, and 9, we should have a slope of 0. Now the same thing is the case for down here. They have exactly the same slope. So we're going to do that same exact thing over here. So at 1.5 seconds, slope is 0, and so forth. So all of these centers will have a slope of 0. Now to figure out what's going to happen here, so this is either going to come up or it's going to come down. To figure out what happens there, I'm going to look in between. So at this like 0.75 area here, this line, if you were to draw the slope of this line, it is slanted down. That means, or you can also think about it as we're heading in the negative direction. It is sloping down, which means that we have a speed that is at the maximum a negative number. So go back up here to find what your maximum is. Your maximum is 1 meter per second. Max equals 1 meter per second. So that means we're going to fluctuate between positive and negative 1. So we're starting with a negative 1, so we're going to put that in there. And then we go to a positive 1, because right here, it's going up now. Now we're going down, now we're going up, now we're going down, now we're going up. So we have this fluctuation between negative and positive, negative and positive, negative and positive, and so forth. So we're going to write that out. So we have positive, then we're down to a negative down here, back to a positive. That should have been, yeah, right there. And then we're back to a negative, and so forth. Now when we graph this out, we're going to start, we are at the 0, so now we're just going to curve this and we're going to slow this guy down, so we're going to curve up, and then that's going to keep going like this, and we're just going to keep our wave going. All right, now we're going to go to our acceleration versus time. Acceleration versus time, we're going to do the same exact thing. We are looking at the slope, but now we're looking at the slope of our velocity graph. So if we start with with this location, we have a slope that is going down, which means we are at its maximum and in a negative way. So the max acceleration, if we go back up to our notes here, we said that the maximum acceleration was 2 meters per second squared, which means that if we're starting with a negative slope, we're going to start with a negative 2. Then we go to 0, and then we go to a positive. So again, that's at its maximum, so that's going to be a positive 2. So right about there. And then we're back to a straight 0 line, and then we're back down to a negative, and this is going to repeat. Again, we're fluctuating between a positive and a negative 2. All right, so then once we get those guidelines drawn, then we're going to go ahead and go back in and complete our curve. This will continue for the rest of them. I'm just going to stop there. We've done over a cycle. All right, next up, I'll put 2. Next up, we have energies. So we have kinetic energy, potential energy, and total energy. Now I said that the total energy was 5 joules. So over here, if we know that the total energy is 5 joules, the total energy is not going to change. It is constant at 5 joules. Last thing that we have here is kinetic and potential energy. If you take your kinetic energy and you focus from what we did with our velocity, no velocity means we have no kinetic. So anytime that you are starting at 0 velocity, that means you are starting with 0 kinetic. And you can use this all the way across. Anytime it's crossing that axis, we have to have 0 kinetic energy. Now, if you are starting at a maximum at -1 or +1, since kinetic energy is going to be that 1/2 mv squared, it doesn't matter if it's positive or negative, it's always positive. So that means we're not going to use this bottom part of the graph at all. We're going to stay at the top. And so at, this is like what, 0.75 seconds, at this location, we are at the maximum velocity. Maximum speed is going to give us the maximum kinetic energy. So all the energy is kinetic, which means none of it is potential. Well, the total energy is 5, so that means all 5 of our joules have to go into our kinetic. And this is going to continue when we go to the second part here. So a little bit past 2, it says that we have a max speed of 1 reached, which means we're going to have a max kinetic energy of 5 joules. So this is going to continue like this over and over and over all the way through. Now, when we graph this out, it's actually kind of nice if you put little guide points here. But this guy is going to curve up and down, and it's going to still give us a sinusoidal wave. It's just that this sine wave is only in the positive direction. And if you look at its period is half as long as the period from before. Now, when we go to potential energy, when all the joules are kinetic, that means that we have 0 joules of stored elastic. If we have 0 joules of kinetic, that means we have 5 joules of stored potential. Because again, the total has to be the same. So once we know that we start with 0 kinetic, that means that all the energy has to be stored. And that makes sense because if you take a spring and you have it stretched at some displacement, the maximum displacement, right before you release it, that speed is technically 0. There's no kinetic. That means that all the energy has to be potential. The spring is stretched as far as you can go. So we're going to start with 5. Once kinetic energy gets to 5, it goes down to 0. And then this cycle repeats. Again, you should continue going all the way through. I'm just going to stop there. Then once you are graphing these out, again, you should have this nice sinusoidal wave here. Why do I feel like I went too far here? I think I got off. Okay. So, let's check. At 3 seconds, it should be at its max. At 2.5 seconds, it should be at the min. At 4.5 seconds, it should be at its max. 5 should be back to a min. 4 seconds, back to a min. Okay, let's try that again. There we go. Alrighty, so again, these guys are going to be opposites of each other. Double check, make sure you have all the same graphs. We have a maximum of 5 joules, a minimum of 0 joules, a maximum of 5 joules, a minimum of 0 joules. Make sure all your phases are correct, and that's it.